When you do mama should be idiot.
Hey,
When you do mama should be idiot.
Baby, what happened?
hello. Are you also new to that? You don't know that you need to meet yourself when you enter. Until I start removing you. I don't know that you need to meet yourself when you enter. Until I start removing you.
This was right name. No, couldn't write my name. I sent it to the group. Wolo shigono. Wolo shi.
But I hate anything that has to do with Zoom class.
Better vision. Oh God, I'm
There are some people who are here who can no longer enter because I already removed them. Because what I'm doing now, I just want to hear noise and I'll just remove you before I start the class. Okay, good morning, everyone. So as not to waste time, so we better just get to it immediately. Okay, not sure you can hear me. I just took a minute. Okay, good morning, everyone. So as not to waste. Now, okay, our first topic, because I'm actually going to be taking you two topics in chemical kinetics, in CHM 101. The first one is chemical kinetics, and the second one is going to be chemical equilibrium. So, but we're starting with chemical kinetics. Okay, we all know that rate of reaction, when you talk about rate of reaction, you're essentially talking about how fast or how slow a reaction is. And the unit of that measurement is concentration per unit time. It now depends on what the concentration, the unit of your concentration and the unit of your time. Because remember, you're saying how fast or how slow, you want to know the amount of concentration consumed per unit time. Was 1 mole consumed per unit time? Was 0.5 mole consumed per unit time? Was 5 mole consumed per unit time? Okay, sorry, was 5 mole per dm cube consumed per unit time? Because concentration is not mole, it is mole per dm cube. So, was 1 mole per dm cube consumed per unit time? Was 0.5 mole per dm cube consumed per unit time? Or 0.1 mole per dm cube consumed per unit time. So when you're talking about rate of reaction, essentially that is what you're talking about. How fast or how slow. And the unit is going to be concentration per unit time. So, and that means you can actually have your rates as mole, since most of the time our concentration is a mole per dm cube. Is a mole per dm. There's mass concentration, but when we're talking about rate, traditionally, concentration per unit time is used because that is the only way you can actually compare across varieties of molecules. Because remember, individual molecules have different molar mass. So, but you can use mole. That makes it's possible to compare rate across molecules. We'll talk about the problem with that also. So, and that's why the units, they are going to be rates. The unit of rate is going to be mole per dm cube, since that is the unit of your concentration. Now, per second, if your unit of time is in second, per minute, if your unit of time is minute, and per hour, if your unit of time is an hour. Now, there are varieties of rate of reaction, but the one that we consider important at this point, because there's average rate, there is instantaneous rate, but at this point, we just want to discuss the instantaneous rate. We want to talk about instantaneous rate. And what does instantaneous rate mean? It means the rate at a particular time. Now, this is important because there is one rule in chemistry that we all know. We know that as the concentration decreases, the rate of reaction also decreases. I'm sure that that's one basic rule that we learned from secondary school. As concentration decreases, rate of reaction decreases. That means that if you're starting a reaction if your starting concentration is 1 mole per dm cube, now by the time the reaction takes effect and the concentration begins to decrease, the rate at the beginning of the reaction is going to be the highest rate in that reaction, because that rate is going to continue to drop as the concentration also drops as the reaction progresses. Now, and of course, we know the reason for that. Remember, the kinetic theory, the collision theory, they are the number of collision, of course, they are the rate of reaction. And the more they are the concentration, of course, they are the collision rate. So that's why, but that's not what is important here. What is important to note is that, because we spoke about different type of rates now, and you can talk about different type of rate because rate of reaction changes as the concentration changes. And you know that concentration will change when a reaction is taking place. If you're starting with 0.1, at some point it's going to get to 0.09, at some point 0.08, at some point 0.075. So it's going to start decreasing. And as it's decreasing, the rate is going to change. Now, the question is, which rate are you now going to use when you're talking about rate of reaction? Which rate is now important? If we're saying that rate changes, if you look at the curve you're seeing here, what it's saying is that if you look at in this case, the blue is the concentration of the product, while the red is the concentration of the reactant. You can see that as the time increases, the concentration of the reactant decreases. And as time increases, the concentration of the product increases. And I'm sure we understand that, of course, as the reaction progresses, you lose your reactant, you make more product. And that is why concentration of the reactant decreases, concentration of the product increases. So now, if you now want to compute using this now, if you now want to compute rate of reaction, remember, we're talking about instantaneous. There is an average rate of reaction. That is the rate of reaction that cut across the whole curve. On this chart, because this is the plot of concentration against time, we have a plot of concentration against time. Remember, rate of reaction is concentration divided by time. Change in concentration divided by change in time. That is your rate of reaction. And that is what you're looking at here. Now, for the reactant, which is red, what it means is that if you look at that tangent, I'm sure that you were familiar with something like that. The tangent is talking about, because in this case, this is a reaction. I think there was a mistake. This reaction should have written here. It's a reaction between hydrogen and iodine to form hydrogen iodide. is a reaction between hydrogen and iodine to form hydrogen iodide. And that is why you can see this is the curve for hydrogen. And this is the curve, red is the curve for the concentration of hydrogen, while blue is the curve for the concentration of hydrogen iodide. Now, as the reaction progresses, the concentration of hydrogen decreases, while concentration of hydrogen iodide increases. And now, if you look at that tangent, since the rate is change in concentration divided by change in time, that tangent is talking about the change in concentration of iodine. Change in concentration of hydrogen divided by change in concentration of, change in time. Now, if you look at this very well, now you are drawing that tangent around a particular time. If you want to do the average rate, you're going to start from the beginning till the end. But in this case, we're not interested. We're interested in the instantaneous rate at a particular time. And that is why, if it was at the beginning, there's something called the initial rate. If you want to do the initial rate, that means you're talking about rate of reaction at the beginning of the reaction. This tangent will be drawn at the beginning of the curve. For the red, it's going to be drawn at the top, while for the blue, it's going to be drawn at the bottom, because that is the instantaneous rate of reaction. That will be the initial rate of reaction. Initial rate is also an instantaneous rate, but it's just that it is a specific instant rate of reaction at the beginning of the reaction, because initial rate is an instantaneous rate, but instantaneous rate doesn't have to be initial rate. Instantaneous rate can be at any point on that curve. It can be at the beginning, in the middle. Somebody just have to tell you the time, and you know that's where you measure. Now, what are the factors affecting the rate of reaction? According to collision theory, chemical reaction takes place only by collision between the reacting molecules. I just mentioned that now. What affects rate of reaction? If you want to talk about what affects rate of reaction, how does reaction take place? That is the starting point. Reaction takes place via collision between the reacting molecules. They have to collide for you to have a reaction. Now, anything that affects their collision, either the amount of collision or the rate of collision, will affect the rate of reaction. And now, what are those things that affect the rate of reaction, that affect collision? Temperature will affect collision, concentration will affect collision, pressure will also affect collision. How do they affect them? And not how they affect collision now. Well, it's the same thing. Whichever way they affect collision, that is how they affect the rate of reaction. Now, temperature, when you increase temperature, rate of reaction will also increase with increase in temperature. Because when you increase temperature, those molecules gain higher kinetic energy and they collide much more. They move much more and they collide much more. If you decrease temperature, rate of reaction also decreases. The same with concentration. When you increase concentration, rate of reaction will also increase. When you decrease concentration, rate of reaction will also decrease. Why is that? Remember, we're talking about collision. If you have a volume of water, if you have a volume of solvent, and say you have 20 molecules there, you will expect those 20 molecules to collide. But in the same volume, if you have 40 molecules, they are going to collide much more. And that means when they collide much more, you have higher collision, then you are going to have higher rates of reaction. The same thing with pressure. When pressure increases, rate of reaction will also increase. Then it's the same thing. If it decreases, rate of reaction will decrease. How? Because when you're talking about pressure, what you're saying is that you are actually like, if you have a fixed amount, say if I have 40 molecules in 10 cm cube jar, then, and I have the same amount of molecule in 5 cm cube jar, you know that there will be much more collision in the 5 cm cube jar. That is the higher pressure. And in the 10 cm cube jar, there will be less collision. Therefore, the 5 cm cube jar, which has higher pressure, will have higher rate of reaction than the 10 cm cube jar. That is how. So higher pressure increases rate, lower pressure decreases rate. Catalyst does not affect the rate itself. The only thing it does is that it changes. It affects the rate. But how does it affect the rate? It affects the rate. Sorry, I made a mistake. Catalyst affect the rate, but how does it affect the rate? Catalyst does not affect the rate. It's the only one. That's what I wanted to say. Catalyst does not affect the rate via its effect on collision theory. No. Catalyst affect the rate by changing the reaction pathway, it changes the reaction pathway to a pathway of lower activation energy. If you have a reaction A going to B, it's possible that there is a pathway where A will go to, okay, if you have a reaction A giving you a product K, there could be a pathway where A will first give you C and D before going to K, and there'll be another one where it can give you T and B before going to K. But what the catalyst does is that it chooses a lower activation energy pathway so that via that rate of reaction will decrease. And therefore, the catalyst does not affect rate of reaction via its effect on the collision of the molecule, but it does so via a change towards the reaction pathways. Now, you see, the nature of the reacting species, I think I'm not sure why I added it, but it's not important. It's not going to be in the note that I'll give you anyway. Though there is actually something to discuss there, but it's not for this class. Now, there's now something called the rate law. There's something called the rate law. What does the rate law, what does it say? At a fixed temperature, the rate of a reaction depends on the concentration of the reactant. So we already said that okay, if we say temperature increases, affect the rate of reaction. So when you now fix temperature, it means that at a fixed temperature, the only thing that will affect your rate of reaction, at a fixed temperature, most of the time, you have your pressure also fixed, really, because you're not going to be changing your jar back and forth or changing pressure. So most of the time, when we're talking about pressure, we are essentially referring to the gaseous reactant. But in this case, it's just about the interplay between temperature and concentration, because the pressure itself is also not going to be of any serious effect. So now, when you fix temperature, the only thing that will affect the rate of reaction now is going to be concentration. Now, at that particular point in time, you can now change your concentration and look at how that change in concentration affects the rate. What does that mean? The rate of a reaction is directly proportional So when you have concentration, all you need to do, you already know that there is going to be a change when you change concentration. You know that there will be a change in rate. If you now want to know what kind of change when I change concentration, is the rate decreasing? It's increasing by 200%. That is very, very important for information. So if it's a lot of information actually runs from that information, that is when you change your concentration, by how much does your rate change? And how do you do that? You have your concentration, say you have concentration 1 mole per dm cube. You look at the rate. You do your concentration 2 mole per dm cube. You look at the rate. 4 mole per dm cube. You look at the rate. You can now compare how when you double your concentration, did the rate double? Did it quadruple? Though it's a very, very important information. Now, it is that information that is actually presented by what we refer to as the rate law. Now, the rate law says that the rate of a reaction is directly proportional to the reactant concentration, each concentration being raised to some power, and this is what we're talking about. For a substance A undergoing rate is going to be proportional to concentration of A raised to a power. Now, you see, when you see that power, that N is what is called the order of a reaction. That power N is what is called the order of a reaction. I will come back to that. We'll come back to what it means. Now, if you remove that proportionality, you want to put your equality sign, of course, that means there's going to be a constant of proportionality. And that K coming in there is what is called the rate constant. It's what is called the rate constant. For a reaction where you have your 2A plus B, that is, remember, the first one we just talked about one reactant. But where you have two reactants, 2A plus B. Now, this is what your rate is going to be. Your rate is going to be K, A raised to power M. M is going to be the order with respect to A, and N is going to be the order with respect to B. Now, that means the reaction rate with respect to A or B is determined by... So now, when you now want to look at this rate of reaction, let's look at this. If you want to look at this rate of reaction, that is the first one where you have your A. That is, your A gives you the product. All you need to do is vary the concentration of the reaction, and look at what happens to the rate. But because this is just one reactant, that is very easy to do. You're not tinkering with so many things here. But now, where you now have two reactants, how do you do that? So it means that what you do here is you keep, there are two reactants here, A plus B, or A and B. If you want to determine the M, because remember, you cannot calculate, if you know the rate, you cannot calculate the K if you don't know the N. More often than not, in this kind of reaction, you will know you can just estimate your rate from concentration divided by time. That will give you your rate in this kind of equation. Because remember, how you do the reaction, you have your reaction, you measure the concentration at the beginning, maybe after 1 minute, you measure the concentration, after 4 minutes, you measure the concentration, and so on. So concentration divided by change in time will give you your rate. But even you cannot calculate your K if you don't know your N. So how do you know your N? What we're talking about now is how do you know your N? How do you know the order of your reaction? That is what we're talking about now. And I said that if you want to know the order of reaction, you look at when you change your concentration, what happens to your rate. That is what you want to see. We'll discuss that in detail, really, because that is actually very, very important to discuss, to your understanding of this course. So now, again, it's the same thing here, but the difference here is that you're having two reactants. You cannot calculate your, even you can calculate your K also here without, you can calculate the rate of reaction by just doing concentration divided by time, but you won't know your K. So you need to know your order of reaction. You need to know your M, which is the order of reaction with respect to A. You also need to know your B, which is the order of reaction with, you need to know your N, which is the order of reaction with respect to B. Don't worry, I'm still going to tell you what order of reaction really means and its impact, because a lot of people look at that thing like it's just one abstract concept. Now, I know I already, expressions such as one and two tell the relation between the, it's talking about this expression 1, and this is the 2. So tell the relation between the rate of reaction and the reactant concentrations. So it's talking about, this is the expression 2, sorry, I forgot to put the 2 there. This is expression 1. So now an expression which shows how the reaction rate is related to concentration is called the rate law or rate equation. So what you have here, that's your rate law or your rate equation. What you have here is also your rate law or your rate equation. We put it in words here. We are writing it in mathematical form here. But of course, you may need to write rate law for varieties of reaction. So your definition is not important. It's you understanding how to write a rate law for a reaction. And again, you can see 2A plus B here. It does not mean that here your M is equal to 2 or your N is equal to 1. No, because order of reaction is not the same thing as the molecularity of a reaction. What you see here is what is known as the molecularity of a reaction. The number of molecules that are getting involved in a reaction. That is your molecularity. 2 for A, 1 for B. But it's not the same thing as your M and your N, because order of reaction is completely different from molecularity of a reaction. And we already said that an expression which shows how the reaction rate is related to concentration is called the rate law. And those two equations are examples. Now look at this. Examples of rate law. For this reaction, you can see the rate law for the first one. Even you can look at that one. It has two molecules, but Kn2O5 is not raised to power 2. It's still raised to power 1. But H2 plus hydrogen plus iodine, those ones are raised to power 1. It's just by coincidence. Doesn't mean that they are the same thing. That one is just plain coincidence. Doesn't mean that molecularity is the same thing as order of reaction. And you can also look at the third one, which is also coincidence. You can also look at the fourth one. One looks at, okay, you can NO2 is 2, is also 2 here. That's just coincidence. And you can look at hydrogen, it's just 1, while it is 2 in molecularity. But essentially, we need to know that the number of molecules is not the same thing as the order of reaction. Even there are times when you will see a molecule in your chemical reaction, but in your rate law is going to be completely missing. I intended to put an example like that there, but I forgot. Because it's possible, just like we have hydrogen and iodine here, you get to rate law, you just see hydrogen. It doesn't apply to hydrogen and iodine. I'm just saying that it's possible, because that is telling you that the order of your reaction is 0, that molecule is not part of it at all. I'm coming back to now. So from what we just showed, it is obvious that rate laws per reaction must be determined by experiment. It's not something you just look at the chemical equation and you write it down. It's very obvious there. You need the experiment to be able to determine. So it cannot be written by merely looking at the equation with the background of our knowledge of law of mass action. However, now, this is very, very important. You see, most of those reactions that you see where your molecularity equals your rate law, equals the order of reaction, they are more often than not what are known as elementary reactions. Elementary reactions. Those reactions are reactions that only take place in one step. They are not reactions that take place in stages. They only take place in one step. When you see your molecularity equal to your order of reaction, more often than not, you're dealing with elementary reaction. And that is why you see what is written there. However, for some elementary reactions, the powers in the rate law may correspond to coefficients in the chemical equation. But usually, the powers of concentration in the rate law are different from coefficient. So, and of course, those for reaction 4 I already explained all those ones. Now, so the order of the reaction is determined by the number of atoms or molecules whose concentration change during the reaction. And these changes determine the rate of reaction. So order of reaction, we already said that is determined experimentally. And now, this is just rewriting what we already written. It is also the sum of the power of the concentration terms in the rate equation law. We already, which is what that's just saying, is just making reference to what you have there, because you're adding together the concentration, because that's what it's still making reference to. So now the overall order of the reaction, remember, here I said M is the order with respect to A, N is the order with respect to B. What is the total order of reaction for that reaction? It's going to be M plus N. It's going to be M plus N. You add the individual order together to give you the total order of reaction. And that is what this is saying. The overall order of a reaction is going to be your N1 plus N2 plus your N3. And of course, it's saying that the order of reaction can also be defined by, which is already explained that. More often than not, you can, not every time you can always talk about the order with respect to the reactant. So examples of reaction order. So in the first one, you can see the rate is equal to Kn2O5. So that means the order of reaction is 1, because that N2O5 is raised to the power of 1. The rate is equal to KH2I2. That means the order of reaction is 2, because that's 1 plus 1. H2 raised to power 1, I2 raised to power 1. So that gives you 2. Rate, the third one, you can see the reaction side is also 2. Then the fourth one, 1 plus 2, that gives you 3. Then you can also have fractional order. I forgot to mention that. You can have fractional order. Then reaction may be classified. A reaction may be classified according to the order. So if in the rate law, if your M plus N is equal to 1, it is first order. Now, in that situation, say for example, if your because that means it's either your M and N, they are half, or they are 1 plus 0. If it's 1 plus 0, for example, if your M is equal to 1 and your B is equal to 0, sorry, if your M is equal to 1, your N is equal to 0, that means that B is going to be completely missing. So that will be B raised to power 0. So that means you won't have B there at all. And that's what I was talking about. That you can actually have a reaction. You can actually have a situation where a reaction is present in your equation, but it's going to be completely missing in the rate law. We'll talk about that kind of situation. Now, the reaction whose concentration now, and this is what we're not talking about because we're there now, is zero order reaction. A reaction whose concentration, because what order is telling you is just giving you in numerical term how much a change in concentration affects your change in rate. That is what order of reaction is telling you. For example, if I double my concentration and if the rate doubles, that is a first order reaction because they are equal. That is a first order reaction. If I double my concentration and the rate quadruple, that is a second order reaction because what happens to rate is double of what happens to rate is double. What happens to rate is quadruple of what happens to what happens to rate is double of what happens to my concentration. Remember, you double concentration, rate didn't double, it's quadruple. When you double concentration and the rate double, that's just 1, really. That means your reaction is the first order reaction. But when you double concentration and the rate quadruple, that means that what happens to your rate doubles what happens to concentration. And that makes it a second order reaction, and so on. But now, for the purpose of this slide, there are reactions when you change your concentration, rate remains the same. When you change your concentration, rate remains the same. Those are what we call the zero order reaction. It doesn't matter what you do to your concentration, you still get the same rate of reaction. So a reaction whose concentration does not affect the reaction rate is not included in the rate law. And those are the ones that I said they are going to be completely missing in your rate law because they're going to be raised to power of 0. And that means they will disappear completely. You won't see them. So a 0, in effect, the concentration of such a reactant has the power 0. Thus, when you raise them to the power of 0, that makes them 1. So that means they disappear completely. So a zero order reaction is one whose rate is independent of concentration. So when you say a reaction is a zero order reaction, what you're saying is that reaction, it doesn't matter what you do to that reaction in terms of concentration, the rate of reaction will still stay the same. So they are referred to as zero order reaction. It means concentration has nothing on that reaction. But for example, this is not an example of a zero order reaction, but we just want to use this to demonstrate because I put this together like quickly in the last I should have, because this may be, but if you look at this, but this is an example of a situation whereby you have a reaction whose order of reactant whose order is 0 in that reaction. Now, for example, you have NO2 plus CO to give you NO plus CO2. At 200 degrees Celsius, the rate equation is this. Now, what this is saying is that, you see, at that 200 degrees Celsius, it doesn't matter what you do to the concentration of CO, the rate of reaction will stay the same. That means the order with respect to CO is equal to 0. And that's why CO is completely missing in that reaction. In that rate law, Hence, the rate does not depend on CO. So this is not included in the rate law. And the power of CO is understood to be 0. Now, that means this reaction is 0th order with respect to CO. It's not a 0 order reaction because the reaction itself, the order of reaction is 2. Because if you want to calculate the order of reaction for this reaction, it's going to be 2 plus 0. Because with respect to NO2, it is 2. With respect to CO, it is 0. So 2 plus 0 is going to give you 2. But the reaction is 0th order. That is the term. The reaction is 0th order with respect to CO. But the total order of reaction is actually 2. Now, when we now, because we're getting to the point, I'm sure a lot of you are going to be like, okay, what is even you see this order of reaction, what does it even tell us? When you say something is an order of reaction, what exactly is it telling us? Or when you write your rate equation, if a molecule is missing in your rate law, if a molecule is missing, just like what we have here, if a molecule is missing in your rate law, what does it really mean? What does it say about that molecule? The one that, because it doesn't mean you can have this reaction without CO. You must, if you don't have CO in that reaction, you won't still have the reaction. CO must be present in that reaction to have that reaction take place. But it's not in the rate law. What does it mean when a molecule is missing in the rate law? What it means is that that molecule is not taking part or does not take part in the rate determining step. It means that particular molecule does not take part in the rate determining step. Remember what we always say in chemistry. I'm sure you learned that also in secondary school. The slowest step of a reaction is the rate determining step. The slowest step of a reaction. And that makes sense. If you have about 3-4 people pulling each other, it doesn't matter how fast the fastest is. The slowest man will still determine the speed because it's going to drag everybody down. So when you have a reaction that takes place in stages, remember I said that there are some reactions who have their molecularity equal to, their molecularity is equal to their order of reaction, that those ones are elementary reactions, that they take place in one step. What we're talking about now doesn't concern those elementary reactions. We're talking about reaction that takes place in more than one step. Now, when a reaction takes place in more than one step, that means some steps are going to be faster than the other. All those steps are not going to have the same rate. But the one that has the slowest step or the lowest rate is going to be the one to determine the overall rate of that reaction. If step A is if the rate is 2, if step 1, if the rate is 1, if step 2, if the rate is step 3, if step A has a rate of 2, if step B has a rate of 1, if step C has a rate of 2, it doesn't matter. You already know that the overall rate is going to be 1. Because when the 2 produces its own, it's going to be slowed down by that step B. Because the step B will take its time. You're just going to have accumulation of the product from step A. Step A will take its time, will use its own one, that rate of 1. That is what it's going to use. Even this one is being supplied at the rate of 2. It will do its own work at the rate of 1. And step C, even that has a rate of that can afford a rate of 2, is not going to be getting enough to be able to process. It's still going to have to process at that rate of 1 because it can only process what has been supplied. And at the end of the day, the overall rate will now be 1. And that's why we say the slowest step determines the rate. Now, any molecule that is not part of that slowest step will not have any effect on the rate of reaction. It can be part of any other step. And that is why you can write a rate law and not have a molecule present in that rate law, but you still need that molecule for the reaction. Because the only reason why that molecule is missing is that it's not present in the rate determining step, which is the slowest step. So it has been determined experimentally that the sequence of steps for a chemical reaction is as follows. So you have the first step is the slow, the second one is the fast. So what is the rate equation and the overall chemical equation? And the overall chemical solution. Now, if you now want to do this, that means to write the overall equation for this, we all know how to do that from secondary school. That means you add this equation together. When you add them together, you're going to have your D. And you're going to have your A plus 2B to give you D. And we are putting slow there to tell you that at the end of the day, though step B is fast, it's not going to be the overall rate. The overall rate is still going to be for that slow. That is what is going to be the overall rate, which is what I explained now. The rate of reaction is still going to be of that slowest step. So now, since the rate of reaction is controlled by the slow step, the rate equation will now be, now when you now want to write your rate law, you are not going to be using anything in that fast step. The only thing you're going to write in your rate law are those things that are present in the slow step. That is how those molecules, you see them in the overall equation, but they are not present in the rate law. It's because they're not in the slow step, they're in the fast step. They are not in the slowest step, so to say. They're in the fast step. So to write your rate law now, your rate law is now going to be, because you have one molecule of A in your rate law, your slow step and one molecule of B. And that's why your rate is going to be K into A raised to power 1 and B raised to power 1. And you can see your overall equation as 2B. But in your slow step, you only have 1B. So your order of reaction essentially is telling you the constitution of your slow step. It's telling you the chemical constitution of your slow step. That is what your rate law and the order of reaction are telling you essentially. Now, we spoke about rate, we spoke about, but remember, most of these things, you can come back and calculate your, if you look at, there's a rate constant here. So more often than not, your experiment will tell you your rate, but you come and determine your rate constant. If immediately you know your rate, you know your A and B, you know your order of reaction, you can calculate your rate constant. But now, we have rate of reaction. Why? And we're still talking about rate constant. So why do we need a rate constant? What is the importance of a rate constant? Now, for all orders of reaction, except zero order, because remember with zero order, the rate always remains constant for zero order. With concentration changes, rate will still remain the same. Now, the rate of reaction varies with concentration. So you're doing a reaction, even for a reaction, hydrogen and iodine to give you hydrogen iodide, the rates will change from the beginning of that reaction till the end. You won't even have a single rate of reaction throughout that reaction. But the rate constant is a constant at any given temperature and is independent of concentration. It doesn't matter what your concentration is, your rate constant. It's called a constant for a reason. As long as your temperature is constant, your rate constant will be constant at whatever temperature at which you're working. So you cannot compare the behavior using rate of reaction because the rate of reaction itself is actually very finicky and subject to changes in concentration. So you can't be comparing. You want to compare two reactions, you can't be using rate. You're better off using rate constant because it does not change with concentration. As long as your temperature is constant, your rate constant is also a constant. And that is what you can use. If you want to check, how fast is a particular reaction, you can only use rate constant. You can't use rate because rate will change when concentration changes, but rate constant does not. So you want to compare two reactions. Which one is faster, which one is slower? You can't use rate. You can only use rate constant because it's not subject to concentration changes. So if the rate constant and the other are known, even when you don't know the rate, you can calculate the rate also. Now, molecularity of a reaction, I've spoken about this. So this is just like, whatever I'm saying here is still going to be like a repetition. But so chemical reaction will be classified into two. You have elementary reaction, you have complex reactions. So I already told you an elementary reaction is a simple step reaction, which it happens in a single step. A complex reaction. So every other reaction that takes place in more than one step, those are called complex reaction. So I already defined molecularity of a reaction. There are a number of reactant molecules involved in the reaction. Thus, the molecularity of an elementary reaction is 1, 2, 3. So that depends on the number of molecules, and we already spoke about that. The elementary reaction having molecularity of 1, 2, and 3. So they can be either unimolecular, bimolecular, or termolecular. So these are examples. You can see the first one, that's a unimolecular reaction because you only have one molecule. You have example there. You have a bimolecular reaction. Those are two molecules in the reactant. You also have the termolecular reactions also, and you have examples of that also. Now, I'd already said that the termolecularity is not the same thing as order of reaction. So the molecularity is just the total number of molecular atoms which take part in the reaction as represented by the chemical equation. And of course, you call them molecularity. So the order of reaction, we already explained that. They are the sum of the power to which concentrations are raised in the rate law. So what those powers, M plus N, those are. So what are the differences between order of reaction and molecularity? So we already said the order is the sum of the powers of the concentration term in the rate law expression. And molecularity is the number of reacting species undergoing simultaneous collision in an elementary reaction. And that is what is in the slow step. So molecularity is an experimental, sorry, order of reaction is an experimentally determined value. We already said that. Why molecularity is a theoretical concept. Order of reaction can be fractional value. Molecularity of reaction, they are in whole number. Order of reaction can assume zero value, but molecularity cannot have a zero value. Order of reaction can change with conditions such as pressure, temperature, and concentration. But molecularity, because those things, because when you change some of those conditions, they can affect the order of reaction, which means they can also, via that, they affect the rate. Whatever affects the rate can also affect the order of reaction. So molecularity is invariant for a chemical equation. So now, how do we now determine order of reaction? So the rate of equation of a reaction with a multi-step mechanism cannot in general be deduced from the stoichiometric coefficient of the overall equation. It must be experimentally determined. The equation may involve fractional exponential coefficient. I already explained all this. The rate equation is a differential equation, and it can be integrated to obtain an integrated rate equation that links. So what are we talking about there? So now, remember we had a rate law. We had a rate law. From that rate law, we can have a differential rate law. We can also have integrated rate law. What does differential rate law mean? Differential rate law expresses how rate depends on concentration, while integrated rate law expresses how concentration depends on time. So we can walk backward from the rate law to infer the steps by which the reaction occurs. So the whole idea, what do we use order of reaction for? You determine order of reaction when you want to determine the mechanism of reaction. That is beyond the using it to determine the rate constant. Order of reaction is actually used to determine the mechanism of reaction. Because most chemical reactions do not take place in a single step, but they result from a series of sequential steps. So now, this is an example of how to determine order of reaction. Now, if you look at this, the following tabulated data refer to a hypothetical reaction, A plus 2B to give you C. Now, if you look at that first, now, let me quickly explain. If you have this now, you want to know the rate constant from this. So what you do, you want to know the rate constant from this. So what you want to do, if you want to determine the rate constant is, number one, you need to be able to write the rate law. You need to be able to write the rate law to know the rate constant. So now, to write the rate law, because remember, your hypothetical rate law is just going to be your rate is equal to K, A raised to power X, B raised to power Y. What is your X? What is your Y? You need to determine that. How do you determine that? Remember, your X is your order with respect to A, while your Y is your order with respect to B. Now, how do you determine that? To determine your order with respect to A, or sorry, let's start with B. To determine your order with respect to B, you hold the concentration of A constant. If you look at experiment 1 and 2, you realize that the initial concentration of A is 1.0 times 1 times 10 to the power minus 2 for the 2. But you now see that for B, we double that concentration from 1.0 to 2.0. Now, that means that we're keeping the concentration of A constant, and we double the concentration of B to be able to determine how change in concentration of B affects the rate of reaction. Now, we now realize that the initial rate, and we are calling it initial rate because this is not just any rate. We're measuring the initial rate. This rate was measured at the beginning of the reaction so that the rate we are going to get will reflect that concentration. Now, when we double concentration, we realize that the rate also doubled. Now, if you now look at experiment 1 and 3, the initial rate of B was also kept constant, while we doubled the initial rate of A. Now, we now realize that the rate changes from 1.5 to 6.0. Now, that means for B, when you double the concentration of B, the rate also double. When you double the concentration of A, the rate quadruple. That is how to determine the order of reaction. Now, how do you now use that to determine the order of reaction? Comparing 1 and 2, this is the rate. This is the rate for 1 and 2. We're talking about B now because the second rate, the second concentration divided by the first concentration. Hold on, what's going on? Okay, this should be 1.5. I was wondering. Okay, sorry. This 1.0 times 10 to the power minus is 1.5, not 1.0, please. So the rate for 1 and 2, now you divide also those one by 2. You now realize that both of them double. That is what is important. Both of them double, really. Concentration double, rate also doubled in response. So now this is how you use that to rate ratio is equal to concentration ratio divided by order. Rate ratio is equal to concentration ratio divided by order. Rate ratio is equal to 2. Concentration ratio is also equal to 2. Now, what is y? That makes y 1. Because 2 raised to power 1 is also going to be equal to 2. And that's the order, how the order of reaction is equal to 1. You do that same thing for A. For A. And of course, when you do that same thing, you're going to get your x is equal to 2. Now, that means the order with respect. That means your rate expression is going to be your k, A raised to power 2, and B raised to power 1. Now, this is your rate expression now. This is your rate law. You already have your rate law. Now, from that, you can now, okay, the question still asks for rate constant. So, how do you now calculate your rate constant? You now use this same rate law now. Now you have a rate law. You can now use this rate law. You just need to come back to this table, come back to that table and just choose any of this information. You can choose experiment 1, experiment 2, experiment 3, but you cannot choose some from 1 and some from 3. But just choose, if you're choosing your initial rate and your initial concentration, they must come from the same experiment. It doesn't matter which experiment you choose. If you substitute them, you're going to get the same rate constant, which is going to be, in this case now, I think, which one was used? Let me quickly check. I think experiment 1, I guess. I think experiment 1 was used. You can use any experiment. You're still going to get the same thing. And remember, for different experiments, you have different concentration. But you're still going to get the same thing because it's a rate constant. They have different rates, but they still give you the same rate constant. And that's why rate constant is the only reliable parameter to which you can compare reaction. Now, and I already said that you have two kinds of rate law: the differential rate law, which shows how reaction depends on concentration, and integrated rate law, which shows how concentration of a species in a reaction depends on time. Now, let us, okay, I would like you to ask questions, please. I need to stop now so you can ask questions. So we'll continue from here tomorrow 10, and we're going to use 2 hours tomorrow, please. 10 a.m. because we have to finish this part because you won't have the time next week. We need to finish, we still have how many slides? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we still have about 20 slides on chemical equilibrium to go through. So now your question, please. Because normally I was supposed to stop at 10 minutes so that you can ask questions. Oh, okay, Moshood, you can unmute. Okay, or is it that you can't unmute? Okay, let me. Okay, I'm asked to unmute. Okay, you can unmute now, Moshood, because I can see your hand up.
Okay, good morning, sir.
Good morning.
So please, sir, I want to ask about the order of reaction.
Okay.
That it can only be gotten. It's not something we can actually hunch to know. So it can be gotten by a chemical experiment. Yeah. So now, if we're actually solving questions on it, are we going to be giving it together with the question?
No, well, the fact that I said it can only be solved experimentally does not mean that when you need to answer a question, you won't be given all the information required. All information. You see, let me. In fact, good question. When we say it can be solved experimentally, remember how you get your order of reaction. You vary concentration, you calculate the rate. When concentration doubles, you want to see what happens to the rate. Now, if coming from that, like a good example is this. It can be determined experimentally, but again, there's a table here where you already have all the information. Now we're able to, where is that table now? Now this is a table. All these are from an experiment. That's what we mean. It doesn't mean that when you want to answer a question, you won't be given all the information needed. Now, all this is what you are going to be doing in terms of experiment. But if you need to answer a question in a theoretical setting or in a theory class, of course, you'll be given all the information.
Okay, sir. Okay, sir. Thank you very much, sir.
All right. Question, please. Please feel free. We should be able to. Normally, I like to leave 10 minutes. So, okay, Ade Goju. I'm trying to, okay, you can unmute now, please.
Excuse me, sir. Will you be sharing the slides with the course reps?
Definitely. That goes without saying. In fact, okay, maybe I will even give the slide before the end of today. Please, class rep, remind, if you don't get that slide before 6 today, please send me messages.
Thank you, sir.
Thank you for that, really. Question? All right, because I want to believe that you have other classes to go, and I don't like to delay students in my class, so they need to. So, okay, Abdul Rahman Baki. Okay, I think you can unmute now. Okay, I can't see him again.
Good morning,
okay.
Sir.
Oh, okay. All right.
Good morning, sir.
Good morning.
I want to know about the, like, if you want to raise to power of any number, how will we know what we be the number? Is it by the mole or what?
You see, that's most of those things we explain. We just okay. Hold on, because normally I like to come back to the slide. I gave this question. When I gave this question, I said you can calculate the rates. You can calculate the rate constant without knowing the order of reaction. And this is the hypothetical equation for so it's raised to the power of x. A is raised to the power of x, B is raised to the power of y. How do we know it? That was the experiment that he was talking about, that this has to be done experimentally. So this is not by mole. This is the whole idea of what we did here was getting that x and y. I'm not sure whether you were not listening. Everything we did here was trying to calculate that x and y.
I'm listening, sir. What I'm saying is that in that reaction, there is like the A plus 2B. So are we going to raise B to the power of 2 because of the mole? That is 2.
And I'm certain, I'm going to repeat again, I'm certain that I mentioned this over and over again. Molecularity is not the same thing as order of reaction. That 2 is the number of mole of B. It's not the same thing. About 3, 4, 5 slides was used to demonstrate this. That 2 is not the same thing as the order of reaction. And if you look at your 2 here, your B at our final answer, what did we get as B for B? Is 1. It's not 2. And for the one that is 1, we got 2. And even before we did this, I repeated this. I don't know. Maybe I repeated this more than 10 times. That molecularity is not the same thing as order of reaction. Molecularity is a theoretical concept. You'll always see them in your chemical equation. But for order of reaction, they are done experimentally. The only time when molecularity equals order of reaction is when you're dealing with an elementary reaction, a reaction that is just of one step. Immediately you're beginning to have a reaction that is more than one step, more often than not, molecular. And when they do, even under that, more often than not, maybe it's just coincidence really. All right.
Thank you, sir.
Question, please. Okay, okay, I can still see questions. Okay. I'm coming. I want to unmute you so you can ask your question. Okay. Okay. Caleb, your question, please.
Morning, sir. Morning, sir.
Yeah.
Please, can we go back to that slide where we got the order of reaction for B? Because you divided the rate, the concentration, yeah, this 0.2, where and the 0.1 and the 1.0. Where did we get it from, please? In the table.
This one?
This 2 exponential minus 2 and 1 exponential minus 2. Where did we get from the table?
Hold on. Which one are you talking about where we calculated the order for B, right?
Yes. Where did we get those values?
You see, this is one of the reasons why you should listen. I told you that there was a mistake here, that this thing was not 1.0, that was 1.5.
Okay.
Because I remember I mentioned that it was a mistake, that this was supposed to be 1.5. This is why you've got to listen every minute of the way.
Okay.
I hope that is clear. All right.
It's clear.
But that still shows that you're paying attention anyway. All right, question, please. Oh, okay. I still have some people trying to. Okay. Ola, Dami, Lola, you can unmute now.
Good morning, sir.
Morning.
There was a question you talked about where you gave us a question concerning nitrogen oxide and oxide, and you were like, it only collide with the power to get the order of reaction.
What do you, please, I can't hear you well. I don't understand what you're saying, because I like to understand.
There was an equation you gave earlier, where nitrogen oxide was adding up with carbon oxide.
Okay.
And you said the order of reaction was like same thing with the power. That was like by coincidence.
Because I think I'm trying to find that slide. You see, sometimes I'm trying to find that slide, because I already know the slide you're talking about, and what you're saying is not even what I said.
Okay, but I just want to ask that, does it mean for us to get order of reaction, we always look for rate law?
You need order. You're not looking for rate law to write order of reaction. You're looking for order of reaction to write your rate law.
Can I question with the you won't crash out?
Who are those people talking? I will start again now, because I really like to attend to this. So, okay, I just a minute. I want to make sure because normally when students ask questions, I like to attend to them appropriately, so that we don't just waste our time because sometimes the question students ask is much more important than. Oh, okay. Now you're talking about this slide, I guess.
Yes, sir.
Okay. Now, what I was saying here, we were talking about zero order reaction here essentially. And let me quickly correct what you said just now. You don't look for rate law to write order of reaction. You're looking for order of reaction to write rate law. Because at the end of the day, you see, you want to write rate law for this. Your hypothetical rate law is going to be rate is equal to K multiplied by concentration of NO2 raised to power X multiplied by concentration of CO raised to power Y. You still need to calculate your X and Y. When you now calculate your X and Y, they now realize that, okay, your Y is equal to 0. So it disappears completely from the rate law. So you now see that is the order that tells you the rate law, not rate law telling you the order.
Okay.
But because when you write your hypothetical, you don't even know what your X and Y is. And that means you don't even have a complete rate law. What you have is just an hypothetical rate law. You still need those values. And you need to go ahead now and look for those orders. Now, in this case, what we're saying was that the order with respect to CO is zero order. And that is why it disappears completely from the rate law. And we already said that what does rate law tells you? It tells you those molecules that are present in the rate determining step. If they are not present in the rate determining step, they don't determine the rate, they won't appear in the rate law. Did I answer your question? If I didn't, let me know.
Okay, sir. So if we're like giving a question to look for order of reaction, is there a way we can do it? Since you said we can only get that experimentally.
Somebody already asked this question. So the problem with most of you is that you don't listen, really. Somebody already, I explained this, and somebody already asked this question. Maybe that was even the first question. Because the only thing, you only listen to yourself. Because there is this table. So what was the purpose of this table? Did we do any experiment here? And when he asked, I also told him, the fact that we said it could only be done experimentally doesn't mean that when we want to ask you a question in an exam, We won't give you all those things you get from experiment. All these values are what you get from experiment. And if I can give you all those values, I'll give you all those values you get from experiment and ask you to calculate order of reaction. And that's exactly what we did here. That means you were not paying attention, even when that question was asked. And that is why when somebody is asking a question, you listen, because it might just be one of those things you are also still curious about.
All right, thank you, sir.
Question, okay. I'm coming to unmute. Okay, we still have Ogunji. Okay. Ogunji, you can unmute now and ask your question.
Good morning, sir.
Good morning.
Yes, sir. So, from the explanation that you have been giving so far, I was able to understand that rate is a measure of how fast or slow a reaction occurs. And
Yeah.
from the preceding slides that you have shown us, be able to see that the rate of reaction, sometimes it can be slow, it can be fast. But now the question is that for us to know how slow or how fast a reaction can be, is it from the reactant or from the product?
You can use either of the two. You can use that. You
Okay.
see, and that's why this chart is important. One, the blue is the product, the red is the reactant, and you can use either of the two.
Okay.
Oh, sorry. So, any other question? Want to see? Okay, anybody? Oh, okay, nobody else. All right. So I'll see you then tomorrow. And good afternoon. Oh, sorry, good morning.